This is Solid in the Wild. Hello. I'm Zoe.
I'm David.
And I'm Mike.
And we're staff engineers at Pivotal Labs. You may have heard this thing where it takes 10,000 hours to be an expert at something. Well, we have 27,000 hours of paired programming combined between us. We have paired with 458 people total. We build stuff for a lot of people. Some of them are media people. Some of them are automotive people. Some are finance people. Relevantly for today, some are e-commerce people.
Over the next half hour, we would like to tell you a story, which is even true if a little embellished. We've changed some details for presentational purposes, but in all the ways that matter, this is a true story about an actual project that the three of us really worked on. The story goes like this. So suppose you're building an e-commerce platform. It's going to include both back-end systems and front-end clients. It's going to manage sales of all kinds of different products. They're manufactured by many different manufacturers. It's going to be distributed by all kinds of different shipping companies. It's going to cross all kinds of different country boundaries, as one does. And then about 6 months into this massive undertaking, you get a phone call from your project sponsor, and he says,
So, what did I buy?
this is a reasonable question. If you've poured a lot of money into a large software project, you'd like to be able to get in and kick the tires a little bit. And it is at this point that your immediate stakeholders then say,
Wouldn't it be great if we actually sold and shipped a product?
the answer to this question is yes. Yes, it would. If you're going to demo some software to the person who paid for it, it's really nice when that software does a thing. But as you consider this possibility, you run into a bit of a conundrum. You see, all the current integrations that you've built into your system so far are, shall we say, aspirational. The particular shipping center in Canada that you would like to ship your product to is going through a modernization movement. They're sunsetting some of their older systems. They're building some new and modern microservices to replace them. And so rather than integrating with any of those old systems that are going away, you have been building against the grand and glorious idea of a future that does not exist. And this means that if you actually want to sell something and ship it to Canada, you're going to have to integrate with a brand new system, a legacy system that's very gnarly, all the experts for which are elsewhere and unable to come and work with you. Also, that demo sponsor is in 8 days. Go. You know this feeling.
Today, we're going to assume you have some familiarity with the 5 solid principles. We're not going to go deep into what solid actually is. We're more interested in sharing with you stories about how building towards the solid principles enabled us to turn to our business stakeholders and say, yes, I think we can do that big gnarly integration in only 8 days. Because there's really only one constant when it comes to building software, and that's change. And there's really only one way to effectively deal with change, and that's by keeping software soft and malleable. So let's jump right in. Like I said, we're going to go through the 5 solid principles in order, but not in this order. For our story, Sodoli works much better. So the first principle in Sodoli is the single responsibility principle. For us, the biggest lesson was how it affected our project structure. Now, that's not what people think of when they think of the single responsibility principle. Most of the time, people think about how one function should have one job, one reason to change. Or one class should have one job and one reason to change. But how often do we think about the responsibility that our packages play? Or the reason why your module might change? We didn't at first, and it didn't seem to be too much of a problem. We had taken our code base and separated it into horizontal technical layers. We had one package that contained all of our controllers, and one package that contained all of our services, and this was fine. If I needed to modify a controller, I knew exactly where it was. It's over there, in the controllers package. If I have to change that service, that's fine too. I know exactly where that is. But it became difficult as we were pulling more and more stories off the top of the backlog, because I'd have to go into each and every one of these packages in order to build in this new feature. I had to basically change the entire code base every time. And it wasn't just me, it was every pair having to change the entire code base. It didn't really feel like we had much organization at all. It made it very difficult for us to work together because we would be introducing conflicts. It was difficult to refactor or change things because each pair would be depending on the code base as they knew it, especially since We had pairs working all around the world. We had experts in Bangalore and experts in Geneva and experts in Bulgaria. And the communication difficulties of those time zones made it really, really difficult. So what we ended up doing was taking our horizontal layers and turning them 90 degrees into vertical slices of business concerns. We ended up having multiple modules, and each module had one responsibility. Everything involving looking up an account was in its own module. Everything involving validating an order was over there in that module. And every module had a vertical slice, everything from the controller all the way down to the database. And this ended up working really well. Each module now did actually only have one responsibility, one reason to change. It made it far easier for us to work together. If you're taking this home for your own code base, the biggest question is, where do you draw the line? From our experiences, smaller modules are greater than bigger modules. Oh, let me advance that slide. Smaller modules are greater than bigger modules. So when in doubt, round down, round smaller. Because it's far easier to fix modules that are too small than it is to fix modules that are too large.
A nice quick way that you can check this is actually just with git. The command show with name only will tell you what files are actually changing. And if everything comes from the same root, the same module, you can see that you've really sliced well. Changes don't have to cut across these different features.
If this sounds familiar, it might be because you've been paying attention to Oliver Gierke, who's been talking about this for a long time. At this same conference in 2012, he gave a talk called Whoops, Where Did My Architecture Go? That talked about this idea. And this year, on Thursday, he's giving a talk about refactoring to a system of systems that extends the idea beyond those module interactions and shows what it means when you need to take your code base even further and what those boundaries do when they're done well. We definitely recommend it. You should check it out.
So once we had things sliced up vertically, we started running into other problems that brought us to D, the dependency inversion principle, which for our purposes really took the form of standardized logic. So to find out what this is, let's take a look at this US sales logic.java. You can see here it's very US sales logic. We use American Express for our payments. We ship with FedEx. The actual logic that we're using is charge Amex and then submit the order to FedEx. And this is something, it's kind of a pattern that had been in place with this code base for a bit, is when we wanted to expand a little bit, handle new things, we kind of cut and paste this code. So when we went to the UAE, we just changed FedEx to RMX, great shipper out there, and we went ahead with it. This had a little bit of a problem, though, when we realized some things needed to change. For instance, what if the UAE has customs laws? Most countries have those, and we've learned something important. It's that customs violations lead to massive fines. Don't break customs laws. So what was the solution that we had here? We moved towards generic standard logic. Standard, like customs violations, lead to massive fines. We actually have a name for this. It's smuggling. So let's look at standard real quick. This is the Edison screw. It is from 1909. It's in every house, most places you can go, in fact. It comes in like 5 different sizes. It's in North America. It's in Europe. It's really flexible because it's a very generic interface. And in the last 10 years, it's taken us from wires to LEDs. That's how much change it affords. So we started standardizing. Which validator or shipper? Well, we didn't know. We didn't want to care very much. We created really generic stand-ins for those with these interfaces. Then we created very generic logic from it, where we take a validator, a payment taker, and a shipper. And if the validator says that it's valid, then we charge and submit every time. Now, it's important to know and remember that injection is not the same thing as inversion. Here is a Spring class, and you can see it has that component, and it has that US customs and that UPS shipper, and that's terrible for France. So if you have a very generic one that takes any validator and any shipper, you'll have a lot better standardized logic. So Spring injects your dependencies, but it's up to you to invert them. That's a good takeaway.
Once we had made this division, we had separated the generic standard logic of the business from all the particular implementations thereof. We found that we could start applying the open-closed principle. We could make our system open for extension, but closed for modification. Over time, over the course of the whole project, it created a mindset, a way that we thought about any kind of new functionality, a model of interaction with other teams, and that was something we called bring your own functionality. What I mean by that is this. Like I mentioned, this particular platform operated over dozens of different product categories, all kinds. And all those different product categories had groups of experts. They were distributed all around the world. We had some in Geneva. We had some in Bangalore. And as you can imagine, with a system of this size, there was no way the three of us, however many hours of pair programming we've done, we're going to be able to build the whole thing. So all those different teams of experts in different parts of the globe, we're going to have to work in parallel, which is fine. It's a great way to try to scale up development. But if you consider the logistics of that, how teams are actually going to add new pieces to the system, new product categories, new integrations, they're going to run into each other all the time, anytime you have a high churn component. Any piece of the code base that has to get modified for many reasons or at many times as people are bringing new things in is going to cause you a huge amount of pain really fast. And sometimes these can sneak up on you. For example, suppose you have a warehouse client. The purpose of this class is to send packaging and shipping instructions to a particular warehouse. So you're gonna post to the endpoint of this warehouse's service a bunch of instructions. But where do you get those instructions? What goes here? Well, maybe you've got some logic that decides, well, we don't want to package up an iPhone the same way that we would package up some eggs, so we will check what the order is, and depending on what kind, we'll get the proper instructions for that kind of thing. This will work okay. Until you have many different people in many different places wanting to add new product categories, because every single one of them is going to have to modify this file, this logic chain. They're gonna have to get into it, and you're gonna have the worst merge conflicts every Monday morning. So we started doing something different. We said, suppose we have a generic idea of a packager, which knows how to get you instructions for a particular kind of order. This is an interface, and you can implement it with things like an iPhone packager. Given an order, it knows how to get you the instructions for that. And now, if I want to add in the logic for getting instructions for packaging eggs, I don't actually modify any files. I just add a new one. I add a new implementation of packager for eggs. That warehouse client never changes at all. If it expects to just get a packager and then ask that packager for instructions, then now when new product categories are added to the system, whoever adds them, no one touches this file. This stays exactly the same. So this idea of bringing your own functionality worked all over the place, whether it was a warehouse, which packaging instructions, whether it was order validators for things like customs, whether it was shipping companies, whether it was persistence, anything that made a particular product category special, we had a place for it in the system. There was a place where it could be brought in and plugged in.
So another nice Git trick that you can use for this is to show name status, and you'll see here, if all you have is adds, you've really got those bring your own functionality slices in good. You need to add things, but not really go back and modify things.
So once we had done that, once we had structured the code in that way, and when we got everyone thinking about the way we would add functionality to the system, not in terms of, oh, we'll just change this code or we'll change this file, but rather, how do we structure the whole thing so that new functionality can be brought in instead of getting changed? It resulted in a much more efficient and scalable interaction model for our distributed teams.
So once we had those things, we had our generic logic, we had our bring your own functionality, we really needed to bring it together, and that kind of brings us to the L of our talk, the LISKOV substitution principle, or as we really practiced it, contract tests. Because we had a lot of ways to ship things, and also we had some modernizing shipping companies. We had some interesting new ways to ship. What does the API for a drone delivery actually look like? Our standardized code didn't care at all. You could bring any one of those shipping companies you wanted, but will they really work? We didn't have a lot of assurance in that, honestly, because we knew that a subclass was an instance of parent class, and so everything that people brought to us definitely fit the interface we needed. And we could trust this. We can trust our compiler and the type to tell us that it works, right? Well, even Haskell's types aren't that strong. That brings us to LISKOV's principle. Barbara LISKOV stated, The subtype requirement, let phi of x be a property provable about objects x of type t, then phi of y should be true for objects y of type s, where s is a subtype of t. That's clear and simple. But what you get is a lot of people will focus on this, because it is the subtype requirement. It's about type t, it's about type s, and it's about the subtype of t. And the compiler checks these things for you, and that's really, really polite of it. But what can't it check? Well, it honestly can't check what's inside of your method signatures. You know, you can tell I put in an A and I get out a B, but you can't tell, does the side effect happen in between that? So we decided to focus on this part of it. It's a property provable about objects X. And how do you prove properties? Well, if you're at Pivotal Labs, you write some tests. And how do you prove properties for a lot of classes? Java actually has a mechanism for sharing functionality between different implementations. So we wrote some abstract tests. Here's one right now. You can see it's an abstract class. Ooh, I have a laser pointer, but it's not working. It's abstract validator. So there's a method. You ask it, give me a validator, and some subclass will. And then also a valid order and an invalid order. And then we could write some tests using those, because there's things we knew about every single validator. Like, for instance, when there's a valid order, the validator should not return any errors. That makes a lot of sense, right? That's very basic. It's very universal. So when we get to an actual phone validator, well, here we go. That validator method just has to construct a validator. It just needs to know how to build one. That valid order needs to know what a valid order looks like for a phone. But you don't actually have to write any particular tests if you don't want to, because the overall generic part of it is already written. This helped us a lot because the teams already knew what to do. They could just keep going until all of the tests passed and then put their keyboards down. I don't know why people say that, because nobody picks up their keyboard to program. We know how our standard code worked because we had already tested it against our own implementations. And so we got to test against behaviors instead of just types. Often this was, the class that we were testing actually hadn't been written yet, and that was really kind of fun. The best part about proving these properties, though, is that you can do it at any time, and you can honestly do it all the time.
If this is familiar, you may have been following J.B. Rainsberger, who coined the idea of contract tests back in the day. He's written a lot of really great literature about it. If you look for his blog, thecodewhisperer.com, you can also follow him on Twitter.
We were feeling pretty good at this point. We had modules that only had one responsibility. We had abstracted out our logic so that these geographically distributed teams could bring in their own special details, and we could prove properties to make sure that those details had the behavior that we expected. But we still had one pretty big problem, and that's that the abstract logic depended on concrete types, which brings us to the final principle in Sedoli, the interface segregation principle. Now, very few people that I've paired with have ever actually brought up the interface segregation principle. So let's explore that together just a little tiny bit. In a nutshell, if I'm consuming an interface that you've built, that interface should be narrowly scoped, so I should have to use all of it. I should care about all of it. If you give me an interface with a dozen different methods, and I only need 2 of them, those extra 10 methods introduce unnecessary coupling between us. If you need to change any of those methods, I need to care about that change. I have to recompile my code, even though I didn't care about them in the first place. Like, let's say you're building out a database, and you're giving me access to this database. And you're saying, Mike, here's everything you could possibly want to do with this database. You can put some data into it, you can get some data out of it, and you can drop all the tables. I don't want that level of responsibility. That's too much for me. Maybe I just want to pull some data out of it, or put some data into it. Or maybe I'm building a large abstract test suite that just wants to clean up after itself after it's done. Get all that garbage data out of your database. These narrow interfaces allow me, the consumer, to care about just the behavior that I need. So for us, as I mentioned, we had abstract logic, but concrete models. We had a generic idea of a product validator that would make sure that each product was valid. And all of our different validators needed to care about what a purse was, needed to care about what milk was. And this was fine at first, but as we added more and more products into our code base, we would have to go back through all of our existing validators and modify them so that they knew what these new types were.
It wasn't especially open-closed.
Or we could have them throw not yet implemented exceptions.
Which is exactly like a LISKOV violation.
So we wanted to ask, how do we build an abstraction between our logic and our data? And it turns out that data models also have behavior. Plain old Java objects have behavior too. Each one of our products had a different structure. For a purse, the only important bit might be who makes it. But for milk, it's very important that we know when that milk goes sour. For a Pojo like this, how do you specify the behavior? Well, with lots of specific interfaces. So we took our broad product validators, tossed them out the window, and had narrowly scoped validators. A brand validator does one thing, make sure that the brand isn't just a bunch of gobbledygook or that space key a bunch of times. And the only thing that it cares about is that with brand is implemented. Purse implements it, so we can have Purse implement the with brand interface. And milk also implements it. Milk implements the with brand interface too, which means we can take our milk class, stuff it into our brand validator, even though neither of them know about each other. Brand validator just wants any product with a brand. Milk knows that it implements with brand. Everything's good. We thought we had a really good idea here, so we tried to expand it. We said, well, our data models are going to have more than one interface, but that's fine. You've already seen classes that implement more than one interface. But we struggled when we hit up a validator that needed many interfaces, like dairy farms. Turns out each dairy farm has a different policy on how close to that expiry date you're allowed to sell it. So in order to validate the expiry date, you got to know what the brand is. So we had a lot of trouble stuffing in just a with brand because the compiler got angry about that get expiry date. Can't fix it by giving it a with expiry type, because now all of a sudden you no longer have a get brand method. What we needed was for the validator to take any type T that extended both with brand and with expiry. That ampersand is an intersection type in Java. It's one of the least used bits of Java generics, but for us, it unlocked a whole world of potential. All of a sudden, we could describe an expiry validator class that had a validate method that took any type T so long as that T extended both with brand and with expiry. And this meant that the compiler knew that our product had a get brand method and that it had a get expiry date method. This might be really gross syntax, but you get really great results. It enabled us to mix and match the interfaces to describe precisely the behavior that we needed. We had a new shipping company, that's fine. The shippers listed the interfaces that they supported. Like our new refrigerated ink that has a whole fleet of refrigerated trucks. That ship method has a with expiry date, because they got to know when that milk goes sour too. And if you have a new product type, that's also fine. You just find the shipper that takes the interfaces that you specify. All of a sudden, we can expand into yogurt and not write any new code. These tiny interfaces gave us flexible behavior, and they let us explore and really lock in the other abstractions that we'd built out.
If you'd like to learn more about this, I might suggest taking a look at the entire Go programming language.
So with all of these things together, what happened in that moment of crisis, when every engineer's worst nightmare came true, and our sponsor asked us,
You can totally build out a brand new integration against a complex legacy system without a co-located expert in 8 days, right?
and we got to say, yeah. I mean, don't get me wrong, building out a high-risk, complex integration at the last minute is not my favorite way to do things, but when we found ourselves in that place, we had a contract test for international product shipments, which provided an executable specification for exactly what needed to be true about that integration in order for the rest of the system to work. There was a team of experts within the company that knew the legacy system for that Canadian shipping center very well, so we gave them a test and asked them to make it pass. Turned out, everything didn't go quite smoothly. There was information that they needed to make that call that wasn't represented in our domain yet. But we had these tiny specific interfaces that provided a concrete way for us to talk about them, about what they needed. They wrote out an adapter that said, we need these interfaces, and we were able to add them into the product types we wanted to send them. In general, that's all we had to do. We added to the system. We didn't have to modify much of anything. All the standardized logic was still true, and all the code that was implicated in international product shipments was isolated to one module anyway. That module had been built from the outset with the idea that other teams would bring in new functionality for exactly this kind of thing, like an integration that we needed to add. So when the experts came back to us with their adapter and it passed the contract test, we sat down in a room with everybody's boss's boss's boss and plugged it together, and it just worked. What could have been a really dark day turned into a really great win. So to recap, we let the single responsibility principle inform our project structure. We organized it in a series of vertical slices, each one dedicated to a specific business problem. Within those slices, we separated the generic logic of the business from the specific details of any particular integration or use case. That made our system open for extension, but closed for modification. The primary way that we added functionality into the system was by adding new parts into the system, adding in new adapters that could plug into that standard logic. Of course, with a lot of different teams bringing in those adapters and bringing in that functionality, we found that we needed to be able to prove that it would actually work. The compile time checks against the interfaces wasn't quite sufficient because there were properties that those adapters needed to have beyond just the interface names. So we captured those properties in contract tests and made sure that any new adapter that we brought in could pass them. This isn't to say that we completely disregarded compile time checks, though. Rather than representing our core domain models in concrete classes, we used a large number of small, specific interfaces. This way, any team working in a particular product category could describe with those interfaces exactly the data that their product type contained. And anyone building out an adapter for a new integration or use case could list the interfaces that their adapter required in order to work. And then the compiler could check for any given product type, whether it was compatible with a particular adapter. All of these things together made a large and complex system flexible, lightweight, easy to extend, and pretty solid. This has been Solid in the Wild. We'd like to thank Pivotal Labs New York for sending us out here once again.
I'm Zoe.
I'm David.
And I'm still Mike.
Thank you all for coming.